Good morning, everybody. Good morning. The nightmare that is chapter 9 is almost over. We got to finish up chapter 9 today. In case you weren't aware, I did post the topics for the exam that's coming up next Thursday, and like half of your exam is chapter 9. Sorry, it's the big chapter, right? So it's got all the things in it. So that's what's going on. All right. So let's knock out of the park energy and momentum. Those are the two remaining things that we got to deal with in chapter 9. Let's see. By way of review, like just kind of going back to what we've learned about energy already, right? We have our master equation, right? And work non-conservative, energy final, energy initial. And like energy final, just this could be, like when we're looking at the final energy state of any system, it could have kinetic energy, and it can have gravitational potential energy, right? Like those are the two main types of energy an object can have. Same thing goes like, and these are like final things, right? And then energy initial. Exactly the same sort of ideas, right? It's just we're looking at the energy it has to begin with, right? Is it moving? Does it have height with respect to wherever 0 is? This is, we learned all this back in whatever chapter this was. So what about objects in rotation? What kind of energy does this wheel have? Kinetic or potential? Kinetic. It's kinetic, right? It's moving, isn't it? Okay. So we write kinetic energy 1/2 mv squared. Wouldn't it be nice if we could do rotational kinetic energy? We'll do it in purple. It's the new thing, right? Wouldn't it be nice if kinetic energy rotational could be written as, we just go Greek, right? So 1/2, okay, instead of mass, what's like the rotational mass idea we talked about last time? It involved the table. Moment of inertia, right? This thing that rotating objects have, right? And they have different amounts of it depending on where their mass is and how they're rotating, all that kind of stuff, right? Okay. So instead of mass, wouldn't it be nice if it were just moment of inertia? So we have the 1/2, we have the mass, or in this case, moment of inertia. And then instead of v squared, omega squared. Good job being careful. It'd be really nice if that's what it was, right? That is what it is, yes. Okay. That way, it's so good. I don't have to derive it for you. But actually, if you just stick in v equals r omega into remember the Google Translate from kinematics? If you just stick that into 1/2 mv squared, you end up with 1/2 mr squared omega squared. And what's mr squared? It's moment of inertia. So it's not that far reduced. But now that we've written this energy in terms of the rotational quantities, this is something that we now need to add to our statements. So it's not enough, okay, that we can't just ask the question, is it moving? We have to ask, is it rolling? Like, is it rotating? There's a difference between this wheel's 1/2 mv squared. The 1/2 mv squared would be its center of mass energy. If this wheel is rolling along the ground like this, right, does it have translational kinetic energy? Is its center of mass moving? Yes, right? The center of mass of this wheel was moving, right? So it has 1/2 mv squared. But does it also have 1 half I omega squared. Is it rolling? Yes. So a wheel that is rolling along the ground has both kinds. It has 1 half mv center of mass squared, right? Like the center of mass of the wheel is moving in a line. But it also has rotational energy, 1 half I omega squared. You could tell that wasn't going to stay. So we have to just we have to add into our list here 1 half I omega squared, omega final in this case, right? And then we would have to include 1 half I omega initial squared, right? Into our consideration for what the energy initial and energy final is going to be. So we'll do some kind of examples of this here in a second, but we need to make sure, right, that we understand sort of the connection here. Now, your book, how does your book do it? Your book will tell you, and it's not wrong, that rotational or angular work. Remember work was force times distance, right? FD was a cosine theta or something like that, right? Okay. In rotational terms, instead of force, what would we put? What's rotational force? I tortured you with it last time. Torque. And instead of distance, like linear distance traveled, what do we use for distance in rotation? Theta. So there is a way to calculate angular work. Like how much work does it take to get something to spin? Well, if you know the torque it takes and you know how far it rotated, you have an idea for what work was done. Now, what are the units of it going to be? Hint, it's work. Joules. Watts is power. Okay? Back here, what units does rotational kinetic energy have? Joules. Right? Even if it's 1 half I omega squared, it's going to come out in joules. Right? Work is work, energy is energy, even if we're using sort of different symbols. I know it's a little bit different because in kinematics it's radians per second and all that, right? Okay? But work and energy, that's joules. Like guaranteed. If you're using the SI units for these, the standard units, it'll come out in joules no matter what. All right. But rotational energy, like what is it, what's its effect on things, and how do we need to consider it like conceptually? I mean, I showed you kind of mathematically how it's done. I want to tackle this in this problem right here. This problem is like a compare and contrast, okay? We're going to do a problem of a bowling ball rolling down a hill and the same bowling ball sliding down the hill. And in one case, it's going to be frictionless, right? The bowling ball literally is just going down the hill without friction. Think of it like an icy surface. And it has to be frictionless because we don't want the bowling ball to roll. We just want the bowling ball to translate. We just want it to move in a line, right? And then we're going to compare that exact same bowling ball, but on a hill where there's enough friction so that the ball will roll down the hill, okay? We're going to do both of those problems. And the first problem with the bowling ball sliding down a frictionless ramp, excuse me, we've done this before. There's nothing new about what I'm about to do. So here's our ramp. Here's our bowling ball. It has an initial position. It has a final position. I'm going to put 0 at the bottom of the ramp. The work non-conservative is 0 because there's no friction in this problem. And I'm going to have energy final. What's the bowling ball going to be doing at the bottom of the hill? Is it moving? Yes. 1 half mv squared. Does it have any gravitational potential energy at the bottom of the hill? No, because that's where we put 0. Right? So we'll just put plus 0. So there's my final energy minus my initial energy. What kind of energy does it have up there at the initial position? Is it moving? No. Does it have potential energy? Yes. Final minus initial. Okay, so what am I left with here? I'm left with 1/2 mv squared minus mgh. I'm going to solve this for how fast the ball is going, right? Compare the final speeds of each ball. So we're solving for v. They didn't give me the mass of the ball. Why not? It cancels, right? Okay. And we move the gh over, so I have a 1/2 v squared. I'm going to rearrange here, v squared, and then 2gh. I multiplied both sides by 2, and then I just sort of rewrote it in that order, because I can still hear my 7th and 8th grade math teacher yelling at me that the thing you're solving for has to be on the left-hand side of the equal sign. I only found out later that they were wrong. They were lying. It's like, you can do it that way, but math doesn't, the equal sign doesn't care. Right? Square root 2, we've seen square root of 2gh before, haven't we? It kind of crops up. Whenever there's no friction and you're just dropping something, how fast is it going? Square root of 2gh. When you don't know the answer to anything, square root of 2gh. Or 42. Either of those answers will be really close to being right. Okay? So everything here in black we've done before. There's nothing new there. We didn't need any of our new rotational stuff to figure that out because the ball wasn't rolling at all. But now we're going to do the case where the ball is rolling down the hill, right? So let's get a new triangle here. Okay. And now I'm going to have the ball starting up here, and it's going to be rolling, right? It's going to have some rolling motion as it goes down the hill. I'm going to have my initial state, again, be up here. I'll have my final state be down at the bottom. I don't know why I'm circling them. I'm just decided to. So I'll come back over here and circle these. All right. 0 still at the bottom of the slope. Okay. And same process, right? I'm going to go through exactly the same process I did over on the left-hand side. Work non-conservative. Okay. Is there any friction in the problem? Yes. What kind of friction is it? This is a rolling object. So it has to be static. Okay? Static friction is a conservative force. Static friction is going to be handled by 1/2 I omega squared. Static friction is what's causing the omega in the first place, right? So it's not, and I know it's a little bit confusing because it's friction. Don't you put it in non-conservative? No. The friction that goes into non-conservative is kinetic friction. Okay? Static friction, we handle that with energy terms. So our work non-conservative is still 0 in this problem. There is no kinetic friction happening. Okay. Final. Energy final, right? Energy final minus energy initial. What questions are we going to ask now? We asked, is it moving, yes or no? So, when the ball gets to the bottom of the ramp, is it moving? Yes. 1/2 mv squared. And you can ask the question, does it have any potential energy there? No, it's at the bottom. But there's another question you have to add on. If something is rolling, what do you have to add on? Is it rotating, right? The question is not just is it moving. 1/2 mv squared, that has to do with the center of mass going in a straight line. But 1/2 I omega has to do with the rolling or rotation of the object. So you have to add on that third, is it rotating? And in this case, when it gets to the bottom, it will be rotating and it will have 1/2 I omega squared. So that's a change. That's a difference, right? So there's my final energy minus my initial energy. So at the initial point, is it moving in a straight line? Does it have v velocity? No, it starts at rest. Okay? So 0. Okay? Does it have potential energy? Yeah, mgh. And then is it rotating? No. So now with the knowledge, You're no longer innocent. Now you know. Rotational kinetic energy exists. And so when we approach problems where we're using conservation of energy, we ask, is its center of mass moving? Does it have V? Is there any potential gravitational potential energy? And is it rolling? Is it rotating? Is it spinning? Does it have omega? Does it have V? Does it have omega? Does it have H? Right? Those are the questions you're trying to answer, both at the final point and the initial point. Okay. What does all this say? 1/2 mv squared plus 1/2 I omega squared plus 0 minus, and then mgh is what falls out of that second term. All right. Can I cancel my m? Can I just come in here and go, oh? No. Yeah. There isn't an m, right? In the middle term. Okay. Yeah, eventually. What am I solving for? I'm solving for the speed, right? I mean, it's like that math joke where like the teacher writes a quiz or a test question, and it's like algebra or a triangle or something, and they put like x over here and they say find x, and the student just circles it and says I found it. I mean, I can solve this for V, but do I know what omega is? No. There's two unknowns in this equation. I mean, assuming I know the height, I know the mass, whatever, right? Okay. What do we do? How are we going to find omega? Have you already forgotten Google Translate? What's our Google Translate to get between V's and omegas? R omega, isn't it? And when we did rolling motion back last chapter, I said whatever the center of mass speed is, whatever the V is of the wheel, we can find the rotational speed using V equals R omega. So for anything that's rolling without slipping, V is equal, why in green? I want it in purple. V is equal to R omega, which means omega will be equal to V over R, right? So we're able to substitute in for omega there, right? We've handled omega. What do we do about the moment of inertia? Yeah, where's the bowling ball on this table? 2/5 mr squared, right? Solid sphere. So I'm going to substitute in 2/5 mr squared. Okay, this is going to get ugly. But have faith, it's going to get better. 1/2 mv squared plus 1/2. And now my moment of inertia from the table, 2/5 mr squared. And then I put in omega squared. Omega is V over R quantity squared minus mgh. And it's like my life is over. Like this got a lot worse, right? Can I clean up anything?
The R's and the mass.
Oh. I now have mass in every term, right? Well, that's nice. You were saying something about the R's. This is an R squared. This is a V squared, isn't it? And why did I cross? Anyway, you get the idea, right? I moved it inside. But R squared on the bottom and R squared on top? Mm-hmm. That's not all.
Oh, the
Twos and twos, right? So what am I left with?
1/5 V squared.
I'm left with 1/2 V squared plus 1/5 V squared minus minus GH. What's 1/2 plus 1/5?
2/7.
Really close. Isn't it 7 tenths? right? 1/5 is 2/10, and 1/2 is 5/10, and 5/10 plus 2/10 is 7/10. If only my third grade teacher could see me now. I sucked at fractions, and I still do. I don't like them. The only reason I got this one right is I had it right here in front of me the whole time. V squared minus GH. Okay, so rearrange GH equals 7/10 g squared. So that means V squared is equal to 10/7 GH, or V is equal to the square root of 10/7 GH. All right. It said compare the final speeds of the ball. So the ball that didn't roll, square root of 2GH. The ball that did roll, square root of 10/7 GH. Which of these balls is moving faster at the bottom? Which is that one? The one that didn't roll. 2 is bigger than 10/7. Okay? So the ball that didn't rotate ended up moving faster at the bottom. When I say moving faster, I mean its center of mass V was bigger, right? We solved here for V. Why? Why does the rolling ball not have as much V? If the height's the same, they started with the same amount of energy. Energy has to be conserved. So they ended with the same amount of energy. Where did the energy go?
No.
Into what? Into making it rotate. Energy had to be used to get the ball to rotate. That was energy that could not be used for getting the ball to translate or to move its center of mass. So one of the things we learned from this example is that rolling requires energy, right? And if we start with 10 joules of potential energy, if there's no rolling, then all 10 joules can get converted into kinetic energy. I'm just making up numbers, right? But if we start with 10 joules of energy, and now 2 of those joules has to be going into rotation, what are you left with? 8 joules for translating. That's going to be a smaller speed. Now, does the bowling ball that rolled down the hill have the same energy as the bowling ball that didn't roll? Yes, they have this. As long as they start at the same height, they have exactly the same energies, no matter where they are. It's simply a question of how much energy is tied up in certain things. For the one that didn't roll, all of the potential energy can go straight into 1/2 mv squared. But for the one that rolled, that potential energy had to get divided up. Some of it had to go into rolling or rotating the bowling ball, and what was left over could be used for getting the center of mass to move. You can see that it gets a little bit scary, but because of how everything lines up, because of our table of moments of inertias, and because of Google Translate that allows us to substitute omegas for V's and stuff like that, it can actually fall into something that's pretty like elegant, right, under that square root. If 10/7 or square roots for that matter are elegant. Why do cyclists, and I use that term very specifically because there's people who ride bicycles and then there are cyclists, right? Okay, you can tell the cyclists because they wear funny clothes, right, and they look really serious, right? Because anybody who's had to ride a bike on any of the roads in Fresno knows you are a dead person riding, right? Because people in Fresno don't look for bikes, right? There's a sign up there by the In-N-Out Burger, Knees and Blackstone. If you're coming the other way down Fryan and you're coming there's a little tiny white sign that says Fresno is a bicycle-friendly community. Lies. I know. Okay, I tried it once and I almost died. But be that as it may, why do cyclists insist on having the lightest weight tires they can possibly have on their bikes? I should say they could possibly afford on their bicycles. More what? Speed? More energy going into translating the bicycle as opposed to getting the wheels to rotate, right? If you made the wheel, instead of being like a carbon fiber rim and lightweight and full of air, what if you filled the tire with concrete? The moment of inertia would go way up, wouldn't it? And so the cyclist would have to apply more torque to the wheels to get them to rotate in the first place. And that's energy that cannot be used to get the bicycle's center of mass to go in one direction. I don't really like sports analogies, so let's do a biology analogy. I will now attempt to draw a gazelle. Okay? You guys know what a gazelle is? Africa, boing, boing, boing. Those are the springboks. Anyway, okay? I'm not going to try to draw the whole gazelle. I'm going to draw the gazelle's leg. What is a gazelle's primary defense mechanism? Actually, the antlers aren't a defense mechanism. They're more for showing off and mating and hitting other guys with. Escape. Escape is the primary defense. If you are food to something else, your primary defense mechanism, twofold, either get away or reproduce fast enough that it doesn't matter, right? So, e.g. rabbits, guinea pigs, that sort of stuff. So what does a gazelle's leg look like? Here's a very bad visual interpretation of a gazelle's leg. Okay? Where's most of the musculature of a gazelle's leg concentrated? It's in the thigh, isn't it? Okay? Up high, where the kind of axis of rotation is, right? In other words, evolution selected for a leg that looked like that rather than a leg that looked like that. Why? Why did these gazelles get eaten and those gazelles didn't? So the mass could be the same, right? What does the leg have to do in order to get the gazelle to go place? It has to start rotating, doesn't it? The hip structure is a rotational joint, right? You're rotating, right, a limb around an axis, right? Which of these two structures has the least amount of moment of inertia? The one where the majority of the mass is concentrated near the hip, the center of rotation. There's like other joints. I'm not a biologist, okay? But here, right, your axis of rotation, here you've got a lot of mass far away from that axis of rotation. That means the moment of inertia for this one on the right is really big. And if it's really big, you have to spend energy getting this to rotate instead of getting the center of mass to translate. And the way you get away from the lion is you translate as fast as you can, right? You want to be able to go from 0 to 10,000 miles an hour in no seconds, right? Elephants just are elephants that they just evolved to crush things, right? It's just, if an elephant's mad at you, I'm sorry, you're gone. Like there's just no ifs, ands, or buts about it. There's those videos of the dumb white people on safari, right? And the elephant like just comes up and turns their thing over, turns the whole car over. Right? They deserve it, right? They were probably trying to Instagram the elephant, and that's my feeling about social media, so why not? Okay, let's do a quiz. All right, the last thing we need to tackle is angular momentum, okay? So we've done kinematics, we've done Newton's laws, we've done energy. Now we've got to do momentum. Momentum in its linear version was equal to mass times velocity. This was, isn't this like the first thing we learned in this new unit or something like that, right? Okay, so the rotational version, wouldn't that be nice? Wouldn't it be great if we could just write I omega? And that's exactly what we can do. Okay? Except we're going to use the symbol capital L.
Oh, okay.
This is not my. Maybe it is my fault. I'm perpetuating it, right? Like I keep the tradition alive, right, or whatever, right? But I'm not responsible for picking any of these symbols. It is what it is. Okay. So yeah. So the angular momentum is just moment of inertia. So the problem is, the big problem is, to do conservation of momentum, we had our final and initial momentums had to be the same. Maybe, I think, didn't I do it the other way around? Your book does final equals initial. I think I like to do initial equals final. It just makes more sense to me, right? That's true for angular momentum. The initial has to be the final. But conservation of momentum is typically happening when two objects are colliding. What's an angular collision? Whatever picture you just got in your head is the wrong one. Don't know what it is, but I can almost guarantee it's wrong. It is not two rolling objects colliding with each other. That's straight up conservation of momentum. Okay? What we need is a rotational collision. The closest thing that I can point you to that happens in real life, everyday, part of our everyday experience is what takes place inside of your car's transmission. Every time that your car goes from a stop to moving or from moving to coming to a stop. Your car's engine doesn't turn off, unless you got a fancy car that turns off at the stoplight or whatever, right? But your car's engine is running, right? Constantly. You turn on the engine, it just runs. But the car doesn't move, right? The car won't move until the car gets put into gear. And then when you let off the brake pedal, you put the car into drive, right? The car will then start to move when you don't hit the pedal. In order to go from not moving to moving, with your engine spinning, right? The crankshaft is going. It has to couple that crankshaft, that rotation, to the rest of the parts of the car that make it go. And the way it does it is through something called the transmission. And inside that transmission is a clutch. And the clutch on one side is a spinning crankshaft ready to deliver power to the wheels. On the other side is a not spinning connection to the wheels. The clutch sits in between and allows the two things to come together and to begin rotating together. Okay? So you got this rotating disc, the part of the engine, okay? And then you have this not rotating thing. They have to come into contact and begin to rotate with each other. If it happens abruptly, the car will go and maybe stall. Okay? But if it happens nice and smoothly, okay, then the car will accelerate smoothly. I hesitate to ask this question. I don't want to embarrass anybody, but let's let some people flex right now. How many of you know how to drive a manual? Yeah, see, the number is dying. Right? Okay? The number of people that know how to drive a manual transmission car. I'm guessing by the time I retire 15, 20 years from now, it's going to be, how many of you know how to drive? Right? Seriously, because there's just going to be, robo-taxis everywhere. So, those of us that drive or know how to drive manual transmission vehicles, right? We have 3 pedals to contend with and only 2 feet, right? What's that third pedal for? It's the clutch. So in an automatic transmission, the transmission figures it out. And most automatic transmissions, contrary to what you might think, are not controlled by computers. They are mechanically driven with pressure, and it's actually some of the best engineering I've ever seen in my entire life. It is incredible, right? You want to go down a rabbit hole? Just YouTube, how does an automatic transmission work? And your mind blown. Like, it's just crazy what these engineers and technicians like invented to make this work without any computer intervention whatsoever. Some more fancy kinds are now computer driven, and you've got like constantly variable transmissions that don't have gears in it. Anyway, it gets crazy. But if you're doing a manual transmission, you're shifting the gears. In order to shift a gear, you have to detach the transmission and the wheels from the rest of the motor, make the change in gears, and then reattach those 2 things back together again. The way you do that's with that third pedal. Third pedal in, it's disconnected. You can take all the changes you want, and then you bring them back together. And part of learning how to drive a manual is getting the muscle memory down to make sure that happens smoothly. Okay, had to replace the clutch in my first car because it happened. Everybody learns how to drive. Replacing the clutch isn't that bad. There are worse things like replacing the water pump. If a mechanic ever says to you the words water pump, all of your money is now gone. Because you have to like disassemble half the car to get to it. It's crazy, depending on the car. All right. So rotational collisions are either like 2 rotating things coming together and starting to rotate together, or they are changes in moment of inertia. I wasn't able to bring my demonstration apparatus today for this, but we'll just kind of have to imagine this one. Ice skaters in the Olympics, figure skaters in the Olympics, okay? One of the things that figure skaters are required to do at certain parts in their program is a maneuver. I never remember what it's called, right? But they'll be skating along, right? Doing whatever, dance, blah, 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 right? Okay? And then they'll throw their arms out. They'll put their leg up like this, right? Okay? And then what do? They're like sailing along. Like, what's the end of this maneuver? What do? They don't jump. Sometimes they usually aren't doing this before a jump. They'll take this form and then they'll pull everything in, right? They'll literally like stop moving in a straight line and start spinning, right? So they went from this, right? Notice where all the mass is, right? It's way out, right? Big moment of inertia. And then they come in and they pull all of that mass in. And what happens to the rate of their rotation? It gets really, really fast. Angular momentum has to be conserved. And things can have angular momentum even though they're moving in a straight line. It's kind of weird, but it's true, okay? As you translate and you pull all of those extremities in, the moment of inertia goes down, and what happens to their angular speed? It goes up, right? So usually, what you're doing with conservation of angular momentum in the angular case, this will turn out to be some initial moment of inertia. Why was that not purple? I thought I hit purple. Initial moment of inertia, initial angular speed, and then some final moment of inertia and some final angular speed. And it's the moment of inertia that's doing all the changing. Okay? So there's some change in where the mass was located that gave rise to a different omega. So that's more what conservation of angular momentum problems are like. So let's see if we can't find, so this is kind of, this is what I was talking about, like things moving in straight lines or whatever can have like angular momentum or whatever. Okay? So let's say somebody comes along and like puts their backpack or bag or lunch or something on the edge of the merry-go-round, right? Okay, and I don't know which way the merry-go-round's going. Let's say the merry-go-round's going like that, right? So like, what does this look like top view? So top view, there's my merry-go-round. Here's my two kilogram package on there, right? And the merry-go-round's going around like this. But we just want to find the angular momentum. We're not doing like initial and final or any of that kind of stuff. It's just, they're just asking me to find the angular momentum, okay? So let's see here. They haven't told me omega, and they haven't told me moment of inertia. Oh, we need a chart? I had a chart somewhere. Where did it go? Thought I had this. Let's duplicate that and let's move it down here. Here we go. And go back here. Okay. So yeah, is there an entry on the table for object sitting on the edge of a merry-go-round? No. Right? There's no, I mean, we can model the merry-go-round, but it's not asking me to find the angular momentum of the merry-go-round. It's asking me to find the angular momentum of the object, right, that's sitting on the edge of the merry-go-round. So we ignore like the merry-go-round doesn't, unless they're asking you to find like the total angular momentum of the system, right? That would be the merry-go-round and the object together, right? But it doesn't say object sitting on the edge of a merry-go-round up here. So what do? If it's not on the table, you either use the table to make the shape of the object, or if it's like a little tiny thing going around in a circle, tennis ball on the end of a string, space station orbiting around the Earth, you treat it as a point particle. You treat it as just a mass going in a circle. And what's the moment of inertia for a mass going in a circle? It's just mr squared. Which is confusing because the thin-walled hollow cylinder is also mr squared. Okay? That just happens to be the same. Notice this is big M, which means total mass going around. If it's just a ball on the end of a string, or an object on the edge of a merry-go-round, or an ant riding on the outside of a tire, or if it's just a single like point thing that doesn't have a spread out mass, you just say it has mr squared. All right. So we got the moment of inertia. We can find that, right? Mr squared. The omega. Did they tell me anything about omega? What did they tell me? They gave me mass, 4 kilograms. They gave me, what's 2 meters? That's the radius, right? Radius is 2 meters. And they gave me tangential speed. They gave me a v. How do I know it's v? Yeah, look at the units, right? Meters per second is going to be v, isn't it? Omega is radians per second, but v is meters per second. So basically what they're saying is this thing is moving tangentially right there at 5 meters per second. So how am I going to get to omega if all I know is v? Google Translate. Right? We can go from tangential v's to rotational omegas through our Google Translate here. So let's see. That means omega is going to be equal to v divided by r, right? So now I can put this together. My moment of inertia is mr squared. My omega is v over r. This can get cleaned up a little bit, can't it? The r's cancel, and I'm left with mrv, which is usually written mvr. Again, I don't know why. But notice this angular momentum right here in the box is written down in terms of not angular quantities. M's, V's, and R's, right? Not omegas, not I's. This in the black box, right, is the angular momentum for a particle, a small object, moving in a circle. So again, tennis ball on the end of a string, right? If you know how fast, like V, tangential V, that tennis ball is going on the end of its string, you can find its angular momentum by just using MVR. The angular momentum of the International Space Station as it rotates around the Earth is going to be the mass of the International Space Station, the tangential or orbital velocity of the space station, times how far it is away from the center of the Earth's core. Center of the Earth, which is the core. So things that are moving, not necessarily in circles, can have angular momenta. I don't have this. I should make this a quiz is what I should do. But let's not do the quiz version. Let's just do the what if version. So I'm going to draw 3 pictures on the board, okay? So the dotted lines represent the path that my particle is going to take. Tennis ball, ant, I don't care what it is, okay? But here's my particle, and it's going around, right? It's like going that way, okay? Does this thing have angular momentum with respect to this point P right here? Why? It's going around in a circle. Here's my point P. Here is my little object. Let's say it's moving, I don't know, that way. Does this object have angular momentum with respect to point P? It's still kind of going around, isn't it? I mean, it's a square, but it's still like going around. Now, over here, this angular momentum would be MVR. This angular momentum is, I don't know. Okay? The radius is constantly changing here, isn't it? Okay? The radius here is the smallest it'll ever be, but then it gets bigger and bigger and bigger, and then it gets smaller and smaller until it reaches its minimum, right? So like, I'd need some integrals and stuff like that to go find like what the angular momentum is at any time during this, right? It's complicated, but the point is it still has angular momentum, right? Here's P. Here's V. Does that particle have angular momentum with respect to point P? Yes or no? How many of you say yes? How many of you say no? How many of you are totally confused? What is angular momentum? It's either I omega or MVR, right? Those are like, we've established 2 mathematical interpretations, right? It can be fairly straightforward to see that this has omega, angular velocity, right? And even this square, yeah, okay, it's got omega, right? Omega's weird, but it's does this have omega? It's moving in a straight line, right? Does it have MVR? It has mass, it has velocity, but does it have a distance, not necessarily a radius, does it have a distance from that point right here? Yes. If the square has angular momentum, then this does too. There's distance right here, right? but there's also distance there, distance there, distance there. I'm not saying the angular momentum's constant. I'm just saying it exists. There is an angular momentum with respect to this point, even for objects that move in straight lines. When you go to open a door, it's a conservation of angular momentum problem because you are walking into the door. Now, are you rotating into the door? No. Hopefully. Depends on how good the party's going, right? Okay. But you're not doing this into the door. Okay. You're walking straight into the door. And as soon as you hit the door, now what are you doing? Are you now rotating? There's a little bit of rotation, isn't there? Now, you don't want to rotate completely into the door, right? You rotate enough to get it out of your way, and then you continue on in some now different straight line path. But you've come up and you've contacted, you had momentum going into the door. And at the instant you strike the door, your straight line momentum can be written down as angular momentum, MVR. And then you and the door together will rotate. And that's a conservation of angular momentum problem. This is best illustrated with those rotating doors that are sometimes on the fronts of hospitals or big buildings or something, right? Where you come up and you hit it and you have to walk around with it and then jump out before you get trapped eternally inside of the door, right? Okay. So even if something's moving in a straight line, can it have angular momentum? Yeah. What's the only way something would not have angular momentum with a point? What's the only picture that can be drawn where this thing would have no angular momentum? If the object was going directly towards or directly away from the point. Okay? It's the only way you can't have any angular momentum. This line passing through point P, there's like no rotation about it. To get really particular, your R and your V have to be perpendicular to each other. And here, the R and the V's are all parallel to each other. Okay? So that's the only time that something would never have angular momentum with point P. You have to be heading straight at the axis. Just like with Emma, right? Emma came up and pushed with all of her might directly into the center. Can't get any rotation that way, right? Can't have any angular momentum either. We didn't finish this problem, did we? Well, we kind of did, right? Because the angular momentum of this object is going to be its mass, 4, times its distance, 2, times its velocity, 5. What's 8 times 5? 40? 40 watts. What are the units of moment of inertia? It's a kilogram, it's an mr squared, so a kilogram meter squared. And what are the units of omega? Radians per second. So that's one unit. But it's also MVR, right? A kilogram meter per second times a radius, which is a meter. And notice, we still get kilogram meter squared per second, right? What's a radian? It's a unitless tag, right? So it all ends up being the same. Kilogram meter squared per second for all of these things. Did that. Okay. One last thing to show you, and I'm not sure this is going to, well, we're going to see exactly how this works. My shoulders will either fall off or they won't. So we'll see what happens. And to demonstrate this, I need electricity. I also forgot my PPE for this one, so if I die, class dismissed. Okay. I won't die, I'll just lose my face. All right. So I have this wheel here, and this wheel is a special physics wheel, okay? Unlike the wheels I've been bringing so far, this one's been altered in that lead weights have been attached to the outer rim, okay? That's because for this wheel and to show you this demonstration, we needed the largest amount of moment of inertia that we could get in the wheel, okay? What I want to do is I want to demonstrate to you conservation of angular momentum to the tune of it doesn't just conserve like the numbers before and after, it also conserves the direction. Let me see if I can't explain. If I grab one side of the wheel, there's like this handle right here, okay? And it's the only part that I'm holding. Do you see how the wheel swings down, right? And goes to its stable position, its center of mass is below the support, okay? So that's when the wheel is not rotating at all. This wheel has no angular momentum. If I try to support it on the end, the wheel just rotates down and then stops, okay? What I'm going to do is I'm going to spin the wheel up nice and fast. And then I'm going to do exactly the same thing. I'm going to grab onto the end here, and I want you to watch what the wheel does. Let's see. Never know. I can't remember which way the Dremel goes. Okay. So if it goes that way, let's give it some beans to start with. This is not what Dremels are for, but it's what we use them for. Okay? Do you see how the wheel is not dropping? What it is doing, though, is it's doing something called precession. Do you see how it's rotating around? But the end of it, okay, is not dropping like it did before when it wasn't spinning, right? Okay? I'm just sort of just supporting, right? Its weight. I wasn't really grabbing onto it. Brandon, I'm going to ask you to do something here, okay? Just grab the wheel. Try to hold it up with both hands, okay? Does it feel heavy?
Yeah, a little bit.
Yeah, a little bit heavy, right? Okay, it's definitely not your standard bicycle wheel, right? Okay, are you comfortable? If I spun this up and have you held onto it, would you be ready to report what you feel? Sure. Okay. No students were harmed in the creation of this demonstration. Okay, it won't go quite as fast. It'll only break some of your fingers. Okay, be really careful. Grab onto that. I want you to try to point the end of this thing somewhere else. What is it? Okay, can you describe what the wheel is doing?
It's kind of spinning when it's...
Does it try to fight you?
Yeah, it's wanting to fight me. It's kind of spinning when I'm pointing it around.
Okay. As he tries to change the orientation of the axle, you feel a force backwards through your arms, don't you? Okay. So I will not... I'm prone to exaggeration, right? Anything to help you guys learn anything. I am not going to exaggerate what I'm about to do, okay? What I'm going to do is I'm going to spin this thing up really fast. I'm going to hold it over here, and then I'm going to move it over here, okay? But do you see how I can do this and my feet stay planted to the floor? Okay, here we go. You ready? The faster you try to move this thing, the harder it fights. This thing has angular momentum, right? It's spinning around. Let's say it's spinning around this way, so its angular momentum is pointed directly at you right now, okay? And angular momentum wants to be conserved so badly that if you try to move it and change the direction of its angular momentum, it will fight you. And that fight, as long as I do it kind of slowly, it's not as big a fight. But if I try to, even if it's spinning slowly, if I try to move it, right? When it was going really fast, I had a lot of angular momentum, and I said change, and it said, okay, but we have to conserve it. So I had to start rotating, right? I was changing the direction of angular momentum, and so it said, you have to change the direction of your angular momentum too. And that's what lifted my feet off the floor. The precession, it's a heavy thing. The precession is caused by a torque that happens. Gravity wants to pull the wheel down, but conservation of angular momentum wants to keep the wheel with its angular momentum pointed that way. So now there's a torque. Gravity's causing a torque, and torques cause changes in angular momentum. So that's why it precesses around. So these tend to end up in like natural history museums or science museums or like the Exploratorium or whatever. And they'll have a much smaller wheel, a little bit lighter, and they'll usually have like a upside down belt sander, something that will spin the wheel up for you. And it's like nice and slow and gentle and probably not going to hurt yourself. And I was at the Seattle Natural History Museum, and they had one of these demonstrations. And there was a long line of kids. Like they were like, first, second, third graders all coming through on field trips and stuff. And they were all having fun. They would spin it up, and then they would take it, and they would jam it against their chests, right? And like their jackets and shirts and stuff just had like melted lines, like, black streaks down the front. I'm sure their mothers were so happy when they got home, right? So they weren't really doing what it was for, right? And they had a seat, and they had different things. You could do stuff. So I got in line, right? First graders and me, right? And when I got up to it, I took one look at the thing, and I said, nah. And I didn't want to use their slow belt sander thing. I grabbed the wheel, and I just spun it up by hand. I just grabbed it and started hitting the side of it to get it spinning as fast as I could. And then I started doing all the tricks, right? I'd pass it around as it precessed, and I did it I was younger then, right? And all these different kinds of things. And then I sat on the chair, and I got the chair to spin around because of the conservation. And all the kids were like, right? Watching this happen. And and I finished, and all the kids went, this is great, right? And the teacher came up. They have such nice people that work at this museum. I don't work here, right? And as that class moved off and I was sort of finishing, another class rounded the corner. Look at it, right? Do it again, right? I was there for like 35 minutes. I couldn't escape. Every time I thought I was done, there was another group coming through, right? I finally saw my chance, and I booked it, right? Because I was tired. This hits you more practically in other ways. Has anybody ever watched somebody try to do like one of those industrial-sized leaf blowers, the kind that you wear the backpack, right? Okay. Have you ever watched how the people using those move? Mm-hmm. They have a funny way of walking. When they rev up the engine, right, the hose, they can move back and forth, right? But they have to walk totally straight. Right? Why do they have to walk totally? Matter of fact, they have to let go of the gas to be able to turn to then go this way. Why? What do they have on their backs? A big fan, right? A big fan, right, on their backs that's spinning around, right? That fan has angular momentum, and it doesn't want to change. It wants to conserve its angular momentum, direction, and magnitude. And so they're forced to kind of walk in a straight line, right? Because it's really hard to rotate their torso because they've got this big angular momentum vector sticking out of their back. For the home user, leaf blowers used to have the fans mounted vertically like this. You'd rev them up. And of course, you have to sweep back and forth, right, to get as many. If you've got a spinning fan and you're going back and forth, this thing's fighting you the whole time. And so the designers got clever and started mounting the fans horizontally. Now, spinning fan, you can do it, it stabilizes it up and down, which is great because you want to keep it at a constant angle, right? But now you can move this back and forth and not have to fight the angular momentum vector. I'm not a very nice person. And the reason I know I'm not a very nice person is because I can't help myself sometimes. If I end up in a big box store and one of the poor employees comes up to me and says, "Can I help you?" Of course you can. See, the problem is I've already done tens of hours of research into the product I want to buy. And they can't possibly know more about it than I do in this moment right now. And so I torture them a little bit. I ask them all kinds of detailed questions, right, that they don't know the answer. If you see me coming and you work at a big box store, run. Just run. So one day I walked in and I needed a new leaf blower, and the poor kid came up to me and said, "Can I help you, sir?" And I just smiled. And I said, "Yes, I'm looking for a leaf blower that maintains its angular momentum vector." And the guy looked at me with that look of, I really wish I had brought my security radio this time because I need security now. You know how in the big box stores they have the aisles and like they stack all the stuff up the aisles, right? And then sometimes the aisles, like, you can't see through the aisle, but you can hear all the marital arguments that are happening in the aisle next door, right, as they argue over paint color or whatever, right? So we were in one of the aisles standing next to all the leaf blowers. And I said this. I said, I want one that maintains its angular momentum vector. And the confusion started in the guy's face. And I heard from the other side, the other aisle, through the, right, couldn't see who it was, but I heard somebody shouted, "He wants one with the fan mounted horizontally." I was like, "Who is that? Who is that?" And around the corner came one of my physics 4A students, right? That had this lecture like 2 weeks before that, right? All grins and proud of himself, saying, "Hey, Mr. Balogh, do I get extra credit?" And I'm like, "No, but you can get me a leaf blower," right? It was amazing. It was fantastic. So have a fantastic rest of the day, and I will see you next Tuesday for what? Exam review. Next Wednesday, we're doing our moment of inertia lab.
Professor, I have a question.
Yeah.
Why did for the initial subscript we change from not to I?
Never mind.